All right. Hello and welcome to this class CS867 QIC890. And this week we'll be talking about the quantum adversary bounds. All right. So this is the quantum adversary bounds are a lower bound technique on quantum query complexity. So they're a way of proving the non-existence of quantum query algorithms. And there's specifically the bound called the positive weight adversary bound is one of the most widely used techniques. So it's incredibly simple to use, and it's just kind of used all over the place. And it's if you only know one trick for proving that there's no fast quantum algorithm in the query model, it should be the adversary bound. So so unfortunately the adversary bounds, the story is a little bit complicated. So there's two different types. There's the positive adversary, the positive, which will denote adv plus. This is a measure of a Boolean function f. And there's the negative one, which will denote adv plus minus. So the negative one, I'm going to call it the negative weight, but it can have positive weights too. So these are measures of Boolean functions. So this is both of these measures. So if f is a Boolean function that goes from 0, 1 to the n to 0, 1, then adv either one of them of f, this will be somewhere between 0 and n. It will be a real number between 0 and n. And so these measures satisfy basically the following, that Q of f is omega of adv plus minus of f, and that adv plus minus of f is at least adv plus of f. Okay, so getting a lower bound either on this measure or on this measure gives you a lower bound for quantum query complexity Q of f. Okay, if your lower bounds the smaller measure adv plus, so we call it a positive weight adversary bound. And if your lower bounds only this one, only this stronger measure, the larger measure, we call it a negative weight adversary bound for reasons we will see. It turns out that the negative weight adversary bound actually characterizes quantum query complexity. So there's this kind of outrageous theorem that says that the quantum query complexity of a Boolean function f is up to constant factors just equal to the negative weight adversary bound of f. Okay, so we'll have to define this measure. So this measure is like it's a different. You can even argue that up to constant factors is just a different way of defining quantum query complexity, but it's a very different way of defining quantum query complexity. It looks nothing like the original definition, and it's kind of hard to work with. And so in practice, working with the positive adversary is much easier. And it's much simpler to deal with this measure. And of course, if you deal with this measure, you only get a lower bound on quantum query complexity. You don't get exactly quantum query complexity. Okay. All right. So this is sort of the kind of high-level overview of what's going on. We have kind of these two different adversary measures, one of which is tight and one of which is simpler to use, but not tight. So let's just kind of go in the other direction. And now, instead of looking at the high level, let's kind of go bottom up and kind of do an example of how an adversary lower bound works. So basically the basic way to use an adversary lower bound, of course, we didn't define this measure yet. We'll get to the definition. But if you want to prove a lower bound on ads plus of f, this will basically look like this. You're going to pick some 0 inputs to f. You will pick some 0 inputs to f, and you'll pick some 1 inputs to f. Okay, and you will represent them as dots here. Okay, and what we will do, so we picked here 3 0 inputs and 2 1 inputs, and what we will do is we will also pick some edges that go between. Okay, so we will have something like this. We will basically put a graph here, a bipartite graph between the 0 inputs and the 1 inputs. Okay, so this you get to choose however you like. You get to choose any set of 0 inputs and any set of 1 inputs, and choose the graph however you like as well. And then the lower bound you get at the end depends on a few things. So first of all, it depends on the degree that you get on the left. Okay, so you can look at the degree of these vertices on the left, the 0 inputs, and you can say, okay, here the degree is 1, here it's 2, and here it's 1. So we'll look at the minimum degree, and the minimum degree is 1. Okay, so this min deg on the left is equal to 1. And we'll do the same thing on the right, and here the degree is 2, and here it's 2. So we will say that the min degree is equal to 2 on the right. And the other thing we need is basically to ask for each bit I. So now we have to ask for each I, in the set 1 to up to n. So basically for each position in the string. For each position I in the string, we want to ask what happens when we filter this graph, remove all the edges where the two strings agree on I. So like, let's say if this original graph is graph G, now we're going to define graph GI, which will be the same graph as G, except we delete all the edges that so and what is an edge here in G? An edge is basically well, it's basically x, y, where x is 0 input and y is a 1 input. So we will say that x, y is deleted if x I equals y I. Okay, so this GI, this new graph GI depends on the index I that we set between 1 and n. Okay, and in this GI we basically delete all the edges that have xi equals yi. So here we're actually finally depending on these strings, not just the graph we defined, but what were the actual underlying 0 inputs and underlying 1 inputs. So here we're depending on basically the allowed queries, like each I defines one allowed query that we're allowed to make. So and then we will look at the left degree and the right degree in the graph G, but instead of taking the minimum, we take the maximum degrees. Okay, so we basically say, okay, so let's say, where should we place GI? So let's say we put GI over here, and GI has fewer edges. Like maybe it looks like this. Okay, it has fewer edges, and we look at the maximum left degree. And here all the left degrees are 1, the maximum right degree, here it's 2. So we have 1 for the max degree here and 2 for the max degree here. And then this is for graph GI. And what we'll do is we will take the maximum overall I of this product. Okay, so we will basically, so what we will do is we'll basically do the max over I of this product of the left degree and the right degree. You know, maybe we will denote this by L of GI for the left degree times R of GI. Okay, so we take the maximum. And then the final bound, so the final lower bound on the adversary is going to be the square root of this min degree, the min left deg, yeah, the min degree left of G times the min degree on the right side of G divided by the max over I of L of GI, R of GI. And all of that is under a square root. Okay, so it looks kind of complicated, but it's sort of, it's also kind of strange that we only define this graph on the inputs, and it felt like we used very little of the properties of the function, but it turns out we actually use enough properties of the Boolean function to define something interesting. So we used, you know, what f evaluates to when we said that the graph has to be bipartite, when we put 0 inputs on one side and 1 inputs on another side. So that has a dependence on what f is. And then we depended on what the allowed queries are. So we depended on the fact that these are actually strings that we're making queries to. We depended on that when we defined the graphs GI according to this condition over here. That basically brought in a dependence on the fact that these inputs to f are actually Boolean strings and we're making queries to them. And the queries should matter somehow. So, so we're sort of, we have some basic dependence on the things that should matter. I think because this definition, well, this is just one way to get a lower bound here on the adversary bound of f. Of course, we would want to maximize over choices of graph G. So in practice, we want to pick the best possible graph G in order to maximize this lower bound on adversary, the ad plus of f. And the best possible graph you can pick is almost the definition of ad plus of f. The only difference is that in the actual definition, you're allowed to put weights on the edges in a way that's slightly complicated. But you know, in the unweighted form, this is basically the definition of ad plus of f. So up to weights, and the weights usually don't matter. This is the definition of the adversary bound. And to understand it, it's best done by example. So let's just take an example function. Okay, so let's take the example where f is the OR function on n bits. Okay, so how do we prove a lower bound? Of course, we've already seen this using the polynomial method, but how do we prove a lower bound on the quantum query complexity of the OR function, right? So we know what we would like. So we know that Q of OR n is omega n, sorry, omega root n rather. Basically because we know that Grover search is tight. This is kind of, well, we've seen in the polynomial method, but also kind of just a famous result that you can even prove directly. Okay, fine. So we know this is what we expect, but let's prove it using the adversary method. In particular, let's prove this claim that adv plus of f is, you know, is at least root n. That, of course, doesn't follow from the quantum lower bound, right? Just because we proved a quantum lower bound doesn't mean we proved a positive weighted adversary lower bound. You know, we have to, it's only one direction. If we prove this, if we prove the positive adversary lower bound, then we would prove a quantum lower bound, but not the converse. Okay, so so how do we prove this? So we should pick a graph. We should pick a bipartite graph. So first, on the 0 input side, well, actually, there's only one 0 input to the OR function. Okay, so we will pick that one. This is the input 0 to the n. Okay, this dot represents the input 0 to the n. Okay, there's only one 0 input, so we know that that's what we want to pick on the left. On the right, what are the 1 inputs to f? Well, every other string is a 1 input to f. But actually, usually in the positive weighted adversary, we're going to want to pick 1 inputs that feel close to the 0 input intuitively, like kind of, it's just a good heuristic that usually we want to pick the one inputs that feel close to the zero inputs. And in this particular case, there's n1 inputs that are particularly close to zero inputs. Those are, the strings that have exactly Hamming weight 1. They have exactly 1, 1. So let's draw them as n dots here. So there's n of them. And this first one is a string 1, 0, 0, 0, 0. The second one is 0, 1, 0, 0, 0, and so on. And the last one is, 0, 0, 0, 0, 1, right? And there's n of these, okay? And we will kind of draw the complete bipartite graph on this, on these sets, okay? So this is going to be G. So we've now defined our graph of G, okay? Now we can, so the first thing we need is the min left degree and the min right degree. Okay, so here the degree of this vertex right here, the degree is n, right? So the min left degree, the min deg on the left, the min deg L or whatever, is equal to n. And here, all of them have degree 1, right? Every point in this graph has one incident edge. So here, the min deg on the right is equal to 1, okay? So that's G. And now for every I, we need to consider the graph GI, right? So we kind of fix I in this in set in a position in the string. And what is GI? So what is GI? GI deletes all the edges. So GI deletes from G all edges except those with xi not equal to yi. Okay, so so except those edges. So the edges look like x comma y, right? So we only keep an edge if xi is not equal to yi. So here I is fixed. So let's say I is 3, just for example. Suppose I is 3. Then we see that over here, our 0 to the n node is now only connected to a single string on the right-hand side. This is the string that looks like 0, 0, 1, 0, 0, 0, 0, where the 1 is in the third position. Because for every other string, then the third bit of 0 to the n and the third bit of any other string, they agree. So all those other edges are deleted. So the graph looks like this. I guess there's 2 above and there's a whole bunch below. Okay, so there's n of them in total, but there's only one edge. Okay, so the degree on the left is now 1, the max degree, I guess. So we have that L of the left degree, L of GI is equal to 1. And on the right, the degrees are 0 except for one string that's degree 1. So the maximum degree on the right is still 1. So R of GI is equal to 1. Okay, the maximum of the degrees here is 1. Okay, now the lower bound that we get is that adv plus of f is at least square root of n times 1 over 1 times 1. Because note that this 1 and 1, this 1 on the left and 1 on the right, was true for every I. So the product of 1 times 1 is 1, and that is true for every GI. So the maximizing over the GIs, you still get 1 times 1, basically, you still get a 1. So we get that the adversary bound is at least root n. Okay, and this because we didn't prove this, but because we are claiming that Q of f equals omega adv plus of f, then we proved a root n lower bound up to constant factors on quantum query complexity. So we proved that Grover search is tight, basically. Okay. All right, so this is okay. So this is how you use the positive weighted adversary bound. Let's do some more examples. So basically, we're just going to do more examples with these graphs, and they're basically all going to be unweighted because unweighted graphs are the ones that most often come up in practice. To formally define adv plus, you have to kind of maximize over all weighted versions of these graphs, and it's actually a little bit tricky to define how we put weights. So we won't do that yet. Okay, so let's do another example. So let's just try to do, well, let's try f equals parity. Okay, this is parity of on n bits, and we've seen already that we know that q of f is going to be omega n, right? So we need to show, we want to show that the plus of f, does it give us the right lower bound? I mean, is it true that this gives us omega n? So we want this to be true, so that adv plus gives us a tight lower bound on the string. And so here, well, we can choose the graph however we like. We need to put we need to choose our set of 0 inputs and 1 inputs that are in play. So here we'll just choose all the strings, right? So this is all the inputs with parity 0. So here we have 2 to the n minus 1 inputs, because we have all of the strings of length n that have parity 0. So that have an even number of ones. And here we have all the strings of length n that have an odd number of ones. And, so that half of them are on the left, half of them are on the right. Okay, fine. The trickier part of the argument will be to decide which 0 inputs are connected to which 1 inputs. And here we don't want to connect everything to everything. What we want to do is connect each 0 inputs only to the 1 inputs that are most similar to it. Okay, and the ones that are most similar to it are the ones that disagree on 1 bit in this case. Okay, so we will connect each 0 input to a 1 input. So we will say that x and y, xy is an edge in G. So we will say that if and only if basically x minus y equals 1, they disagree on a single bit. Okay. So then note that for each string, if you flip any of its bits, then its parity changes, right? So you take any string and you flip any of its bits, then you get a string with a different parity. So that means there's n neighbors to every node on the left and n neighbors to every node on the right. Okay, so the min-deg here is equal to n, and here is also equal to n. Okay. So we can basically already write like adv plus of f is at least square root of n times n divided by something that's going to depend on the graph's gi. Okay, so now we need to look at what happens for gi for any index I. And for any index I, for let's say I equals 3, again, just for concreteness. So suppose I equals 3. What happens? Well, before each string, so like before 0 to the n, for example, was connected to all the strings like 1, 0, 0, and 0, 1, 0, 0. And so before it was connected to all of these strings of having age 1, because it's connected to every string that's distance 1 away from it. So that's in G. So in G, that was the case. But now when I equals 3, then all of these edges get deleted except for 1. So actually, we have 0 to the n is connected now only to 0, 0, 1, 0, 0, 0. Okay, so now 0 to the n is connected to only 1 string on the right. And sort of by the same argument, because G only connected each string to the n possible bit flips, single bit flips of that string. And here, basically, GI will force bit I to be the one that flipped. only one edge survives that's incident to any node. So basically, I'm claiming the GI looks like this. GI looks like a bunch of it's a matching basically, where here you have 0 inputs. Here you have all the 0 inputs, and here you have like, so if you have 0 input x here, then here you would have x to the I, where I'm using x to the I to mean flip bit I of x. Okay, and here, so now if it's y here, then you would have y to the I. You would flip bit I of y. Okay, so you'd have a matching like this with 2 to the n minus 1 on each side. Okay, and so the degree of everything on the left and everything on the right is 1. And so the product of the max degrees is still 1. And maximizing over I, it's still 1 because this is true for every GI. And so basically we get n times n divided by 1 times 1, which is n. So we get that the adversary bound of f is n. Well, it's at least n. It's also, it's always at most n, so it's exactly n in this case. And therefore the quantum query complexity of f is omega n. So we've reproved this as well. Okay, so now let's try just a slightly trickier example. Okay, what's a slightly trickier example? So there's an example called permutation inversion. So here, f is a function that goes basically from n to the n to 0, 1. So we have non-Boolean input alphabet. And basically, we have a promise. The input is a permutation, which means that every alphabet symbol occurs exactly once. And then the task. The task is determine if position where the 1 occurs is in the first half of the string, is within the first half of the string. So for example, if the input looks like 5, 3, 4, 1, 2, then here f of this string is, let's say, 0 because the 1 is not in the first half of the string, whereas f of 1, this is a 1, 1, 3, 2, 4, 5 is equal to 1 because the 1 is within the first half of the string. Okay, and in all cases, the promise is that the input looks like these strings, like it's a permutation where every character occurs exactly once. Okay, so we would like to prove a quantum lower bound on this. So we'll use the adversary method. So what we'll do is we need a set of 0 inputs and a set of 1 inputs. So the 0 inputs, let's take all the strings, and we'll take so all the strings with a 1 on the left, and on the right, and for the 1 inputs, all the strings with a 1 on the left. Okay, fair enough. So when do we connect? When do we want to connect a 0 input to a 1 input? And the answer is when we will want to connect them when they are sort of as similar as possible. That's usually the answer. In this case, what does it mean to be as similar as possible? Well, any 2 strings here must have Hamming weight at least, Hamming distance at least 2. They must differ in at least 2 positions, because if you differ from a string in only 1 position, you cannot still be a permutation. So you cannot still be in the promise. So we can't just say, oh, all the strings of distance 1 away. So instead, we'll say the strings of distance 2 away. Okay, so we say that x, y is an edge you know, if X and Y differ in 2 positions. So what does that mean? So in particular, X here, it will have a 1. So X will have a 1 somewhere over here, somewhere on the right, on the right half. Like, let's say this is the half, and Y will have a 1 somewhere on the left. Okay, and so what's going to happen is that because they disagree in only 2 positions, one of those positions will be this one, which is this position here, and the other one must be this one, which is this position here. So they must agree on all the rest. So like 2, 5, 6, 3, 2, 5, 6, 3. Okay, and then if this remaining thing is a 4 here, then it must be a 4 there. So we've just exchanged the position of the 1 and 4. Okay, to get from one string to another, we just exchange the position of a 1 with something on the other side of the dividing line. Okay, so we connect a pair of inputs if they look like this with each other, right? If they look like we only flipped switched the 1 away to the other half, okay, with a single swap. Okay, so this is G. So this, we define G. And now the question is, well, so first of all, how many, what is the left degree? What are the degrees of all these nodes on the left and on the right? Okay, and the degree of a vertex on the left, we can see that, well, we have like n over 2 different positions that we can move the 1 to, all right? So we can, if we have a string on the left, like this string over here, then how many strings is it connected to? Well, we have 3 choices here of where we can flip the 1 to be. So we have n over 2 choices in general, and therefore there's n over 2 neighbors for each vertex here. So the min degree over here is n over 2, and on the right is also n over 2. Okay, and then the next question, as usual, is what does GI look like? Okay, so let's fix I and ask what does GI look like. And let's just assume I equals 1 for simplicity. Okay, so what does GI look like? So what does GI look like? So here's GI. Okay, so the strings on the strings on the right over here, they have a 1 in the left half of the string. Okay, so the strings on the strings that have the 1 on the left half, but it's not in the first position, strings like this, for example, the 2, 1, and other junk, those strings cannot have any neighbors, because all the neighbors of this string on the other side have the 1 switched over somewhere else, but those strings disagree with this string in position 2 and position, you know, some position greater than n over 2. Okay, so such a node becomes isolated in GI. Okay, a node where the 1 on the right, so a node on the right where the 1 is not in the first position, it becomes an isolated vertex, so its degree is 0. A node that looks like this, though, a node that has a 1 in the first position, a node that looks like this, then you can flip this 1 to n over 2 different positions, and the resulting string will disagree on the first bit with this string. So therefore, a node of this form will have degree n over 2, okay, on the right. So the maximum degree on the right in GI is like this maximum degree on the right is n over 2. What about on the left? On the left, well, on the left, the situation is a bit different. So on the left, we have a 1 somewhere on the right-hand side of the half, okay? And we only care about strings that are adjacent to it in G and disagree on the first bit. Okay, so they disagree with it on this bit. But the only way to do that is to flip this 1 to the first position. Okay, so there's exactly one string that looks like that. And therefore, every node on the left has degree exactly 1. Okay, and so we get L of Gi is 1. Okay, and this turns out to be true for every I that's less than n over 2. And for I that's more than n over 2, then we would get n over 2 on this side and 1 on the other side. So the n over 2 and the 1 will flip. So the product of 1 and n over 2 stays just n over 2. And basically what I'm saying is the conclusion is that the adv plus of f is at least square root of n over 2 times n over 2 over n over 2 times 1, right? Which is square root of n over 2. Okay, and therefore we get that Q of f is omega root n. Of course, you can also achieve root n by using Grover search to find the position of the 1, basically to just imagine that the 1 is a single marked element and every other element is not marked, and you can use Grover search using root n queries. Okay, so that's the basic gist of this adversary bound, and that's kind of how it's used in practice. Just people come up with these graphs. Now, it also turns out that the adversary bound is extremely nice mathematically. So the adversary bound, well, it has many equivalent forms, many equivalent definitions. So one definition is basically the graph definition we've seen, except you put weights on everything. So the definition is slightly tricky. To define to define adv plus of f, what we do is it's the maximum over graphs G, but it's weighted graphs. So actually, we will have the 0 inputs and 1 inputs. And we will have some bipartite graph. Okay, whatever. Okay, and we can put weights on these edges. Okay, like 2, 3, non-negative weights. Okay, and they don't have to be integer, any weights that you want. Okay, any real non-negative weights. The degree then will be the sum of the weights of the incident edges. Okay, so the degree here is 2 and the degree here is 6 and so on. And so then you calculate the min degree on the left. And on the right. And there's a special thing that happens in the restricted graphs GI. So in the graphs GI, well, of course, many edges are deleted. So you're left with fewer edges, maybe something like this. I don't know. Fine. In the graph GI, instead of just keeping the weights as they were, I don't know what these weights are, but okay, suppose there's something like this. Instead of just keeping the weights, you basically get to rebalance them across the two sides in a way that depends on I. So for each GI, you'll have a left weight and a right weight. So you'll have like a left weight here for this 1x and for this I. It's different for each I. And So like if this is the input X and this is the input Y, you'll have a right weight. And it will also depend on the edge, this edge itself. So it's basically, you know, it needs to depend on where it's going. So you'll have this complicated set of weights, and the sort of the requirement is that if you take the product of these left weight and the right weight is at least 2, if the original weight in G was 2 for this edge. So we had this original weight 2 for this edge in G, and now for GI we get to kind of, we are allowed to put, sorry, the square root of the product. The geometric mean is at least 2. So now we're allowed to rebalance this 2 and turn it into a 1 on this side and a 4 on this side. Okay, so if we want, we can make it such that the left degree here of this particular X is 1 instead of 2, at the cost of making this, the right degree here of Y equal to 4. Okay, and we can do this rebalancing for each edge separately and for each GI separately. Okay, and sometimes this rebalancing is useful. So sometimes you will have a bunch of like, you have some weird situation where this looks really heavy like this, like it has all these edges and it's really heavy, but you rebalance some load off of it to other vertices basically. Okay, so strange situations occur where this weird graph by graph rebalancing is useful. It's kind of rare in practice. Okay, so the full definition is in the notes. It's kind of like almost too messy for me to even write it down. But it involves, you know, a complicated set of weight schemes where you both have weights for the original G, and then separately you have more weights for each GI. So it's kind of a big mess. So that's one way to define the positive weight adversary. But there's actually another way, a couple other ways to define it. So there's this spectral form. The spectral form says that adv plus of f is the max over these matrix gamma of, this is the spectral norm of gamma, the maximum eigenvalue of gamma, or the maximum singular value of gamma, I guess, divided by the max over I of the norm of gamma Hadamard product di. All right, where, okay, here gamma is this big matrix where you have well, you basically have all the inputs. This is like the domain of F is indexing the rows and columns. Okay, so like you basically have DOM is basically DOM F by DOM F matrix. Okay, and it must have the property that if X, if f of X equals f of Y, then gamma of xy equals 0. It must have this property. Okay, and also gamma of xy is at least 0 for all xy. Okay, so we have this matrix that has these weird properties. It's basically a matrix storing the weights in the bipartite graph, sort of, not quite. But you can think of it, roughly speaking, as storing the weights of the bipartite graph. So maybe 1 if there's an edge and 0 if there's not. Okay, and then there's this operation. So di is the matrix. It's a DOM F by DOM F, domain of F by domain of F matrix, the same shape. But di as a matrix at position xy is equal to 0, 0 if xi equals yi, and 0 if they're equal, and 1 if xi does not equal yi. Okay, so this is di. Di is basically the matrix that tells you how to get from G to Gi. It basically tells you which edges to keep. So the Hadamard product here is the entry-wise product. So when I'm saying gamma circle di, I mean multiply entry by entry, not like a matrix product, but just multiply the entries to get a new matrix where, you know, the xy entry of the new matrix is the xy entry of gamma times the xy entry of di. Okay, so basically this matrix here, if gamma represents the graph G, then this matrix here will represent the graph GI. Okay, so that all looks similar to before, and the only difference is instead of taking left and right degrees and maximums and minimums or whatever over the degrees of the nodes on the left and right, we're taking spectral norms. So this is taking the largest singular value of the matrix gamma and the matrix, so basically of the graph G and of the graphs GI, okay, the maximum graph GI. And we're not taking square roots anymore. So basically, yeah, that replaces the square root of product situation. It replaces it with just the spectral norm. So it's kind of weird. Weirdly, this ends up being exactly equal. It's not trivial to prove. This is exactly equal to the previous definition. Okay, but it's only exactly equal to the previous definition if you have this constraint. Okay, that the entries of gamma are non-negative. Okay. The definition of adv plus minus of f is the same as above, but gamma xy can be negative. Okay, that's why it's something's called the negative weighted adversary method. Gamma xy can be negative. And then this is no longer, no longer, it's no longer equivalent to a weighted graph formulation. Okay, so formulation. So this is I've said before that it's not trivial to see why this spectral norm situation is the same as that square root of products of left degree and right degree and whatever. It's non-trivial to prove that it's the same. If the weights are negative, though, it's just not the same. So if the weights are negative, the right way to define this measure is using the spectral norm definition, not using the weighted graph. If you do it using the weighted graph, you don't get this measure. You get something that's basically nonsensical because it involves a bunch of divisions by 0. So, you know, yeah, you'll basically get a measure that can be infinity or something. You're not going to get something sensible. So the negative weighted adversary bound only has the spectral form and not the weighted form. The spectral form, though, is very hard to use in practice. So because of this, the negative weighted adversary bound is hard to use in practice. So it's hard to directly analyze the spectral norms of these matrices. It's much easier to analyze these degrees of the graphs, as we've already seen. And to convert to the degree of graph formulation, that only works when you know that the entries of gamma are going to be non-negative. Okay, so placing that restriction on gamma, that's an additional restriction on gamma. And of course, this is a maximization program. So putting a restriction on gamma, putting this restriction here, can only make the final value smaller, the objective value, optimal objective value smaller, because we're adding a restriction to a maximization problem. Okay, so this is kind of removing a restriction here. The add plus minus is a relaxed problem, and therefore it's larger than or equal to. Okay, so just from this from these two definitions, it's clear that this add plus minus is larger than or equal to the add plus. Okay, and add plus for non-trivial reasons turns out to equal the other definition, the weighted form, the graph form of the add plus. Okay. All right. So this is one. So this is basically the definition of the negative weighted adversary bound. As I said before, it turns out to exactly characterize quantum query complexity. But as you can see, it's really not clear where that came from and why. Like this is just a ratio of spectral norms of matrices And why does that have anything to do with quantum query complexity? Where did the queries even go? Where did the quantum go? Yeah, nobody knows. It's just kind of magic. There's complicated proof that this is equal to bounded error quantum query complexity up to constant factors. It's not even equal to exact quantum query complexity. It's equal to bounded error quantum query complexity. If you change the error, then it's no longer true that this is equivalent. So there's something really magical specifically about bounded error quantum query complexity, that it has this characterization, and no other quantum measure has it, and classical query complexity doesn't have it. Something very magical is happening exactly with bounded error quantum query complexity. Right. So I also want to mention that, what happens when we take a composition of functions, like if we take f compose g, as basically, if f is a function from 0, 1 to the n to 0, 1, and g is a function from 0, 1 to the m to 0, 1, then f compose g is this function where, we take f, well, f compose g is going from 0, 1 to the nm to 0, 1. And the way it's defined is basically we take f and we plug in there's n copies here of g, each of which takes m copies. So here, this is like m, and this is like n. So the final string at the bottom is length n m. Okay, and so this defines a Boolean function, which is the composition of f with g. So it turns out that these measures adv plus of f compose g and adv plus minus of f compose g, they compose perfectly. So adv plus of f compose g is equal to adv plus of f times adv plus of g, and adv plus minus of f compose g is equal to adv plus minus of f times adv plus minus of g. This is non-trivial to prove, okay, but it turns out to be true. Okay, so because this characterizes quantum query complexity up to constant factors, we get that quantum query complexity of f compose g is equal to theta of q of f times q of g, which is a really, really nice result. This is a composition theorem for quantum query complexity. It says quantum query complexity just composes perfectly. This is false for randomized. It's false for randomized query complexity, but only by a log loss necessary. So the log loss is necessary. So you must lose logs both in the upper bound and lower bound for different functions. Some f and g's forces you to get an extra times log factor, and some f and g forces you to get a divide by log factor. But we don't know if you ever lose more than a log factor. So it's false up to log factor, open for randomized query complexity. So it's open to prove something like this for randomized query complexity. So let me just write down what's open. What's open is to prove that R of f compose G is, is this true? The lower bound is open. The upper bound is known with a log loss. Is this true, basically? R of f times R of G over something like log n. So this is open. We don't know. You need to lose something like a log n because we have examples where that happens. But we don't know if you can prove that that's the only loss you can have. So interestingly, for quantum query complexity, we know here more than for randomized query complexity. So we know this theorem for quantum query complexity. We cannot prove an analogous thing for randomized. This was open for a long time. Finally, people come up with a counterexample, but it's only by a log. So if you don't care about logs, it's actually still open. So we still don't know what's going on with randomized query complexity. And I should mention, even the log factors, it's for partial functions. So if you care about only total functions, it composes perfectly. Maybe R of f compose G really is omega R of f times R of G for total functions. That's still open as well. So for quantum, this is true for total, for partial, it's just always true. So this is just a really nice theorem, even for partial functions. And even in the upper bound direction, you never need an extra log factor. Anyway, I won't get into that too much, but it's kind of magical that this is true. And it's because of this characterization, the negative weight adversary method characterizes quantum query complexity, which again, we won't prove. But because of that characterization, then then this theorem follows. So I'll say, well, we won't prove it. It's in one of the readings. One of the papers proves it. Okay, maybe one more thing I wanted to mention is that the adversary bounds, they can be, both the positive and negative ones have characterizations in terms of semi-definite programs. Okay, if you don't know what that is, I guess that's okay. But both of them are semi-definite programs, which means that we can take the dual. And they're both maximization problems. They both tell you to maximize choice of gamma, I guess, for example, the matrix, or choice of graph. So they're both maximization. But if we take the dual, we get an equivalent measure, which is a minimization problem. And this is useful to prove upper bounds on both of these. And you can actually, if you prove upper bounds on the negative weighted adversary bound, you actually get quantum algorithms out of it. And this is sometimes done. But it's also useful to prove upper bounds on the positive weighted adversary bound, just to rule out the possibility of easily proving a lower bound. So it's easiest to prove a lower bound using the positive weighted adversary, but sometimes you look for one and you look for one, you can't find one, and then you can rule out the possibility of succeeding with the positive weighted adversary bound by upper bounding this measure, right? By upper bounding ad plus of f. So the formalization as a minimization program says basically, so this is the minimization definition. The minimization definition says pick weight. So pick a weight QXI for each. So this is a non-negative weight for each x in the domain of f, and each I in the numbers 1 through n. Okay, so we pick a non-negative weight for each string and each bit of that string. So for each bit inside each string, we pick a weight. So the total number of weights is so total, n times 2 to the n weights. If f is total. So basically, otherwise it's n times domain of f. Okay. So, and then constraint. The constraint is that for all x and y, such that f of x does not equal to f of y, we must have the sum over I such that xi does not equal to yi of root of qxi qyi needs to be at least 1. Okay. This is the constraint. The constraint is basically saying, all right, if you take any 0 input and any 1 input, if you take 0 input x and a 1 input y, then you should place enough weights on the bits where they differ. Okay, so the bits where they differ are the bits I and the sum. The sum goes over the bits I where they differ. And you better place enough weights on those bits. Place at least weight 1 on the bits to kind of intuitively say, oh, your algorithm must distinguish x from y. It must behave differently on a 0 input and a 1 input. So you must kind of, in this kind of weird weight scheme, we're saying instead of an algorithm must distinguish, we say you must distinguish using weights. So you must place enough weights on 0 inputs and 1 inputs, on the bits of them. And it should be kind of the same bit. So you should kind of pick the same I and X and I and Y and give the same weight to both in order to contribute to the sum. Like if one of the two weights is 0 here, then this product will be 0. So this is kind of a way of saying, all right, you want to distinguish X from Y here. You better put some weights on the bits where they disagree. Of course, it doesn't have to put weights on the bits where they agree. If we imagine the weights to be something like queries, then of course, it doesn't help to query in a place where X and Y agree. Okay, so this is the constraint, and then the objective value. Objective value to minimize. The objective value to minimize is the max over X of sum over I of QXI. So this is basically, we're basically saying now, all right, what is the maximum number of queries we made on any input X? Where basically Q of XY, I imagine it's saying how many times did I query bit I inside string X? And that could be a fractional number. So I can say, okay, I made half a query to bit I inside string X. So when run on X, imagine I have an algorithm and say, okay, when the algorithm is run on input X, it queries position 3 half of a time, okay, whatever that means. So then in total, and it queries position 4 5 times, fine. So in total, across all the positions, when it's run on X, it makes 20 queries. Right? And when it's run on Y, it makes 30 queries. And the maximum is 50 queries. And so I want to minimize this maximum number of queries that it makes on any input. So this is the objective value to minimize. And so this minimization problem defines add plus of F, even though it's obviously, well, it's very non-obvious that you get the same definition as before. So there's another way to define the positive weighted adversary bound. And it's a good way to get upper bounds on the positive weighted adversary bound, because any feasible solution here, if you just kind of show that your weight scheme is feasible, because it satisfies the constraint, and you calculate the objective value, then you get there immediately an upper bound on the adversary bound of F. Okay, and we can come up with some simple upper bounds. So one upper bound is that for a total function, add plus of F for a total function is at most square root of C0 of F, C1 of F, okay, if F is total. Okay. And so to prove this, to prove this, we can look at, we can just define a feasible weight scheme. So we could say, all right, Q of Xi, how shall we place the weights QXI? We can say QXI equals, 1 on bits I inside a cert or certificate of X, and 0 on other bits. Okay, so basically, if the string is, 0, 1, 0, 0, 1, 1, 0. Okay, this is the string. And suppose those 3 bits over here together form a certificate. Okay, then our weight scheme is we will give this bit a 1, this bit a 1, this bit a 1, and we will give all the other bits weight 0 in our weight scheme QXI. Okay, so this sequence of strings here will be QXI for different i's, and this 1x. So here x is this, and qx is basically this. Qx is basically this vector. Okay, so QXI is gives you the weight here. Okay, where this is a certificate. This highlighted portion is a certificate. Okay, and basically the idea is if x and y you know, have f of x does not equal f of y, you know, then the certificates the certificates must disagree. So it's not possible that I can find a proof that the input is a 0 input and a non-conflicting proof that the input is a 1 input. I mean, any proof that the input is a 0 input must conflict with any proof that the input is a 1 input, because or else I'll have a string that can contain both proofs, which is clearly ridiculous. So it must be the case that any proof that the input is 0 input must conflict with any proof that the input is a 1 input. So if I take the certificate inside x and the certificate inside y, if x and y have different f values, those certificates will overlap. And in fact, they will contradict each other. So they will overlap. So what we get is, if this is x and if y has a different f value, then, you know, suppose y is some other string. I don't really care what it is. Whatever, it's the string. Then whatever its certificate is I guess I didn't make it the same length here. I wanted length 7. So let's, all right. So whatever the certificate is for y, let's say it's this one, it must overlap here with 1 bit of the certificate for x, all right? Or else it's not possible for both of these things to be certificates. Okay, so now the weight scheme gives y these weights. So what happens is here, q of xi times q of yi is equal to 1 for a bit I of overlap. Of overlapping certificates. Okay, which means that the sum over all I such that xi does not equal to yi of square root of qxi qyi must be at least 1, because there's at least that one I where the certificates disagree, and for that one I, qxi and qyi are both 1. Okay, so this satisfies the constraint. Okay, it satisfies the constraint. All right, and then we have that that, you know, the sum from y equals 1 to n of qxi, this is just equal to the number of ones in that weight scheme for x, which is the certificate size for x. So this is the C of f comma x. Basically, it's the cost of certifying x within the with respect to the function f. Basically, so the maximum of this over x is equal to C of f. So it's not quite what we wanted, but we can rebalance the weights here. We can basically divide all the weights on the left by like all the weights for 0 inputs, we can divide them by C0 of f, and all the weights for 1 inputs we can divide by C1 of f. And if you rebalance the weights carefully, because we only ever look at products here of kind of a weight on the 0 input and a weight on a 1 input, both for the constraint we only ever look at such products. If we kind of multiply all the 0 weights by the weights for 0 inputs, we multiply by some scalar and divide the same scalar on the one side. I guess that's basically what I'm saying. Multiply these weights by some scalar, divide these weights by some scalar to balance it out. Then you can basically replace this maximum C of f by what becomes the square root of C0 of f and C1 of f, the maximum certificate size for 0 inputs and the maximum certificate size for 1 inputs. So by the rebalancing trick, you can get it to be that. So, you know, of course, that's a little bit smaller than C of f, because here C of f is the maximum certificate size. It's the max of C0 and C1. Okay, so the max is a bit larger than the geometric mean. Okay. So that's called the certificate barrier for the adversary bound. So if your function has small certificates, you will never prove larger lower bounds than square root C0 C1 for a total function. Okay, this is called the certificate barrier. It's one kind of way to immediately know the positive adversary bound won't work. And another way to know the positive adversary bound won't work is called the property testing barrier. And I'll just briefly sketch it. The property testing barrier. So this is better for partial functions. This says if, you know, for all x in f inverse of 0 and all y in f inverse of 1. So all 0 inputs and all 1 inputs, all pairs of a 0 input and a 1 input. If for all such things we have x minus y is large, like let's say bigger than d, okay, then the adversary bound of f is at most, I think it's n over d. The notes have the right, I don't remember if it's, I think it's just n over d. So in particular, if every 0 input in the promise is very far from every 1 input in the promise, like n over 2 far or something, then we get that the positive weighted adversary bound is going to be only a constant. Okay, and therefore we cannot prove a lower bound on quantum query complexity that's better than a constant. And so this is a big barrier for some partial functions. It's never a barrier for total functions because this can't really happen for total functions. This d can only be like 1 for total functions. But for partial functions, sometimes we care to prove a lower bound, and yet this tells us that the positive weighted adversary bound will only ever prove a constant lower bound, which is pretty bad. So this happens, for example, with the collision problem. So I think the notes go over that in a little bit more detail. Let's see. So one last thing that seems to be here in the notes and that I didn't mention is basically a primal formulation for the negative weighted adversary bound, which can in principle be used to construct quantum algorithms. So maybe we will deal with this later on in the course. I won't sketch it now in this video, but you can read the note for just a rough sketch of what this minimization program for the negative weighted adversary bound looks like. Okay, so I think I will stop here. So a lot of things were not proven this week. We kind of mentioned a lot of things that we didn't prove. So I did kind of link to some papers that contain some of those proofs. But yeah, it's just unfortunate that there's a lot of kind of cool technical math here that we won't have time to get into, because it's I guess it's not too important to know if you believe the final results here. It just sometimes it's good to see the proof to fully believe the final results, to fully believe the equivalence of all these measures, or to fully believe that the negative weighted adversary bound really characterizes bounded error quantum query complexity. It's kind of hard to buy unless you really go through the proofs. But going through the proofs takes a very long time, and even though I assign them as readings, I'm not sure if I don't really expect you to actually be able to read through all of those complicated proofs. So that's too bad, but if you're interested in more details, you're definitely welcome to read it on your own, or and ask me questions on Piazza about it, or do a course project about it. So just as a reminder, you will need to come up with project ideas pretty soon. We will talk about it in the live meeting, and I will probably exchange emails with some individual students about this as well. All right, so I will see everyone on the live meeting.